Welcome to the Alain Guillot podcast, a podcast about life, leadership, and money matters. Our guest today is Jeremy DeSilva. Jeremy is an associate professor of anthropology at Dartmouth College, and he is a paleoanthropologist specializing in the locomotion of the first apes and early human ancestors. Today, we will speak about his latest book, First Steps: How Upright Walking Made Us Human. Jeremy, thank you so much for joining us today.
Thank you, Elaine. It's really good to be here.
So the first question is very simple. What is a paleoanthropologist?
A paleoanthropologist, like myself, is an anthropologist. Anthropologists study humans. We're interested in all the different ways that all the different complexities of being human, both past and present. But a paleontologist studies the fossil record. And so as a paleoanthropologist, I study fossil humans. And so my research takes me to Africa, where most of the early human remains have been discovered, caves in South Africa, lakeshore environments in Eastern Africa, where I help find, but then assist with the analysis of fossils found by other teams of researchers. And that's been going on for, the discoveries have been going on for almost a century now.
Okay, so I wonder if we could go a little bit into your past. At the beginning of the book, you said that at age 6 you wanted to be a scientist, and then you mentioned a few careers that you wanted to evolve into, and finally this is the one that you choose. Could you take us onto that process? How is it that someone wake up one day and says, "Oh, I know what I'm going to do for the rest of my life. I'm going to look at all bones and write about it."
Right. Well, I took a very convoluted path to get to where I am today. I never studied anthropology in college. I didn't take a biological or paleoanthropology course at all. And so I tell my students now that they don't need to know what it is they want to do for the rest of their lives as 20-year-olds. Sometimes you discover a little bit later, and that's what happened with me. I've always been fascinated by science. I knew I was going to be a scientist in one way, shape, or form, or would write about science or contribute to science literacy and scientific information somehow. After college, I worked at the Boston Museum of Science, and I really rediscovered my passion and love for science there. I was an educator there, and so it turns out was my future wife. So I met my wife at the Science Museum. The Science Museum was a really special place for me, and it was where I discovered for the first time these ancient human fossils. And of course, I'd known about evolution, but I hadn't really taken that deep dive into the topic. And I was able to do that at the Science Museum as an educator. If you're going to teach about something, you really need to understand it and learn it. And so as I started learning about human evolution, I became obsessed. I was just hooked, not only on the fact that these ancient fossils tell us in general about the big changes that happened in the human lineage over time, but every single fossil that we find is from a once living, breathing, thinking creature, a lot like us, who had hopes and dreams and cried and laughed and had a family. And so I really gravitated to this idea that through scientific analysis, by really asking the right questions and searching for evidence to test ideas, we can retell the stories of these ancient ancestors of ours, sometimes with extraordinary levels of detail. And so that's what really hooked me on this science. It was by teaching about it at the Science Museum. So I eventually left the Science Museum and started grad school, and began at Boston University, and then University of Michigan is where I got my PhD. And now I teach at Dartmouth College and try to instill that same level of excitement about these ancient bones to my students.
Okay, well, I'm gonna get a little bit off topic here. One thing that struck me is that you were an educator earning $11 an hour. I mean, mind you that that was 20 years ago, but that's That's not a lot of money.
No, and trying to live in Boston at the same time. Oh, we were so poor. Yeah.
Wow.
Well, look, it's a nonprofit, and
Okay.
the
That-
Boston Museum of Science is a nonprofit institution, and the educators that work on the floor, they do it because they love it. They're not doing it because they're getting paid a lot to do that. And I see that too with public school teachers. Public school teachers are amazing, and they work so hard, and they don't get the they don't get the credit they deserve. They don't get the paychecks they deserve, as far as I'm concerned. And so one of the things that I've been trying to communicate as I talk to folks about this book is that, look, this pandemic has hit a lot of people really hard. And one of the places that we don't often think about are our science museums. And science museums are such special and important places that help a community come together around this wonderment of our world, and critical thinking skills and science literacy, and being able to combat misinformation, which is rampant right now. And science museums are really struggling right now, because of the visitorship that's been down. And so if you can support your local science museum, please do.
Okay, so I'm going to ask you one more question about that. I have been in science museums in the past, and as a regular person without a deep understanding of history and paleontology and all these artifacts from the past, when I walk into a science museum, I feel so lost. I mean, I see,
Mm,
let's say, a vase that is 5,000 years old, and I just look at it for, I don't know, 10 minutes. And, you know, some scientists spend a ridiculous amount of hours
yeah.
displaying this vase just so I could glance it for 5 seconds and say,
Yeah.
and move to the other side. So I wonder how can visitors like me who don't
Mm,
know much about science can get a better understanding of the things. For example, the skulls that you have behind you. Okay, I have seen them in science museums and I go, and move to the next one. Perhaps for you that would be fascinating.
yeah.
But how could science museum do a better job of engaging the attention
Yeah.
of a layperson like myself?
So, I'm not a museum educator anymore, and I'm sure there are best strategies for this. One of the things that I always thought worked really well was the one-on-one personal interaction that you could have with a museum volunteer or a docent or a museum educator, um, who will approach you as you walk up to that ancient human skull or that vase, and say, hey, what do you notice about this? Or do you see that crack right there? That actually is because when it was discovered, they used dynamite to discover it, and that's why it has that crack in it. And of course, scientists don't do that anymore. And so you can use all these little these little factoids, these little tidbits, these little interesting pieces of information about the discovery of the object, or what the object tells us about our past in general, or what the discovery tells us much more specifically about that individual object. And there are always these amazing stories. I tell my students all the time that bones and fossils tell stories. And we as scientists try to figure out what those stories are. And then as educators, we try to figure out how to tell those stories in the most gripping way that makes the learner want to know more. So it sort of serves as this gateway into much bigger conversations that you can have about the implications of those objects and what they tell us about us.
Okay, perfect. I will make a note on that, and I will next time I go to a science museum, I'll try to have a different mindset, more of a inquisitive mindset.
Yeah.
Let's go into your book. Okay, so you study uh, these old skeletons. Why, in particular, walking? I mean, it feels
Mm,
like you have narrowed your lens to this particular human activity as opposed to, it's like, where do we come from? Why here, there, or so many questions, but you have focused in just that one in
yeah.
particular.
Yeah. So the reason is twofold. The first is that as we look at the human fossil record and we try to figure out the order in which things evolved. Humans are different from apes and chimpanzees and gorillas in a number of different ways. We've got larger brains, we have language, we walk on two legs, we have smaller canine teeth, we use stone tool technology. Our ancestors did. Now we can, fly helicopters on Mars. So we have these differences, and it's only through the fossil record that we can really figure out the order in which those differences accumulated. And what we find as we examine the ancient fossils, go back 4, 5, 6, 7 million years in time, what we find is that the very first thing that changed, the first thing that sort of set us off on our own path, was the way we move. Moving on two legs is the most ancient human, or hominin, ancient human ancestor, characteristic there is. And so it has these deep roots. It sort of sets the foundation for everything that comes later. And the other reason that I find it fascinating is because it's not a common form of locomotion. That if we look in the mammalian world, you see mammals that swim and mammals that fly, mammals that leap and spring, mammals that hop, mammals that sprint, but most mammals just move on all fours. Humans are the only mammals that always walk on two legs. And when we see another mammal do it, when we see a bear move on two legs or a gorilla at the zoo move on two legs, we lose our minds. We videotape it, post it to YouTube, it gets millions of hits, it shows up on the news. And so something that we do every single day, and we even have a word for it, we call it pedestrian, right? It's ordinary. It's not something we think about much. And yet in this book, what I try to do is demonstrate to the reader that it actually is an incredibly fascinating form of locomotion. It has this wonderfully interesting evolutionary history to it, and it sets the foundation for all of these changes that happen later, brain size, dietary changes, how we parent our children even, that we celebrate as being uniquely human.
Okay, you mentioned all the disadvantages of being hold on, I'm gonna bipedal. That's the one.
That's right.
You mentioned all the disadvantages of being bipedal. We are slower, we are not strong. First of all, can you enumerate them, and then what are the advantages?
Yeah. So one of the fascinating things that my research that I've sort of thought about as I've investigated this question of upright walking in our ancestors for the last 15 years or so is that this is not a really good form of locomotion. We are exceptionally slow mammals. The fastest human ever, Usain Bolt, topped out at about 28 miles an hour. In kilometers per hour, what would that be? Maybe 40 or so, right? Do I have that about right? My math might be off on that, but yeah. 28 miles per hour. And that's half the speed. More importantly, it's half the speed of a galloping zebra, antelope, lion, or leopard. We are really, really, really slow. And that would disadvantage our ancestors on an environment or in an environment that's full of predators. And sure enough, what we find in the fossil record are examples of ancestors of ours who were eaten by ancient hyenas and ancient leopards, ancient saber-toothed cats. And so we were vulnerable on that landscape. In addition to that, we are particularly susceptible to injury. We are not optimized for moving in this way. We are just good enough to move from point A to point B, but we suffer all sorts of problems in our bodies as a result of evolution essentially converting an ape that was really good at climbing in the trees and had a mobile foot and flexible knees and hips and other joints of the lower limb, converting that into something that then is moving on two legs on the ground. So who among us hasn't had an ankle sprain or knee problems or lower back problems? Oh, those are the worst. Foot problems, plantar fasciitis, bunions, hammer toes, all sorts of problems that we get because of how we move. In addition to that, childbirth is exceptionally difficult in humans because of changes to the pelvis that have happened that make walking more efficient. And walking is possible, but it changes the shape of the birth canal so that a baby can't just smoothly be born as happens in chimpanzees and gorillas, and instead it has to corkscrew through the birth canal. And it ends up being born most of the time. There's variation here, but most of the time it ends up being born backwards with its head facing in the other direction. And so how have humans solved these problems? We've solved them culturally and socially. So humans don't give birth alone. We always have someone present helping, midwives, for instance, and that I think goes back to millions and millions of years ago, to Lucy's time, as inferred by the shape of her pelvis. That her pelvis tells us that there would have been rotational birth in her babies. How have we solved the problem of all these injuries that we suffer from? I think it's because we help each other out. When somebody's injured, we don't leave them for dead. We get them help. And we can see in the fossil record evidence of healed fractures. So one of my favorite fossils is a fossil of a leg bone that's about 2 million years old, and it's a healed leg fracture. This is long before hospitals and doctors and even controlled fire or buildings, and yet this individual survived that fracture. And I can't see how that could have happened unless they had some help. And so coinciding with our upright walking, I think had to be this aspect of sociality and even some degree of care and compassion for one another. And so that helped buffer the disadvantages, but then there are all these advantages as well. And the most important of them is the freeing of the hands and the upper limb, that you don't have to use your arms and your hands anymore for locomotion like a dog does, or a cat, or a monkey, or even to some degree a chimpanzee and a gorilla when they're knuckle walking. And now with these freed hands, we can be creative. We can make stone tools as our ancestors did millions of years ago. Later, what we see is evidence of symbolic representations of thought, necklaces and artwork that we so celebrate. Being on two legs also changes our exposure to the sun. And so there are what we call thermoregulatory advantages, that we don't have this big sort of platform against which an equatorial African sun would be in contacting with its rays, and so it's easier to cool down if you're moving on two legs. So that could have some advantage as well. And all these ideas have fed into hypotheses of why we started moving on two legs. We're also energetically incredibly efficient, moving from point A to point B. We're not fast, but we can cover great ground and not use much energy.
Wow. Okay. So I'm getting, because we work on two legs, we had our use of our hands that inhibit creativity, and maybe we had to develop a bigger brain because now we can do things and create, and that the sum of all that becomes the advantage of walking on two limbs.
Eventually, yeah. And what's interesting, what the fossils show us is that walking on two legs, again, is ancient. We find fossils that are 6 million years old, right at the base of the tree, of the branch of the tree leading to us. That's around when the last common ancestor of humans and chimpanzees existed, right as the split was happening. And we're already finding things that are adapted for moving on two legs. But brain size increase, so that's 6 million years ago. Brain size increase doesn't happen until about 2 million years ago.
Wow.
So there's this long period of time when we have bipedal ancestors like Lucy and her kind, walking a lot like us, but they haven't had that brain expansion yet. And so these are things that don't evolve in concert with each other. But walking on two legs, again, I think sets the foundation for that brain increase. As we start to increase our range, gather food resources from a variety of different sources, And with that increased sort of energy from all these different foods that we're accessing on the environment, those individuals with slightly larger brains can fuel those brains and they actually survive and do okay.
So you mentioned, wow, 6 million years ago,
Yeah,
there were those discoveries. But if you had to guess, how old are we? I mean, those are the fossils of 6 million years, but
yeah.
probably we were older than that. I mean, this is a wild guess. I'm not gonna hold you to that.
No, it's okay. One of the great things about the science of human evolution is that we can address questions about our origin and where we come from using different lines of evidence. And so I'm talking to you about fossils, but then there are geneticists who have been collecting DNA data from chimpanzees, gorillas, orangutans, and humans to ask that same question. And what they find is that if you look at the differences between our DNA, between us and our close ape relatives, they can estimate that the common ancestor of humans and chimpanzees lived about 6 million years ago, 6 to 7 million years ago or so. And so then the paleontologists like myself will investigate fossils found in that time period to see, okay, well, if that's the case, then we should begin to see things that are that have characteristics that we would identify as human-like in these ancient ape-like ancestors of ours, and that's exactly what we find. And so we have these two lines of evidence, DNA and fossils, converging on that same story. And so the oldest members of the human lineage, what we call hominins, they wouldn't be humans like we understand them today. They wouldn't be Homo sapiens. They would be much more ape-like, especially from the neck up. But unlike modern apes, they would walk on two legs, at least occasionally. And their bones tell us that. They're hip bones, and we have some toe bones, and there's even a skull that would sit on the rest of the body in a way like it does in humans, where it's vertical. The neck comes out of the bottom of the skull rather than out of the back, like it does in some other animals. But we are desperate for more fossils, and so every year my colleagues, go back out there, and we search and search and search and search, and we keep finding these fragments and these pieces that help us put together the human story.
If you had to speculate, why is it that the birth of humanity was in Africa? Why not Asia?
Mm.
Why not America? Why not North
Sure.
Europe, for
Yeah.
example?
Yeah,
Why
no,
Africa?
it's a great question. It's a fantastic question. The evidence that we have from the ape fossil record, if we go back even farther than that, and we say, okay, 7, 8, 9, 10, 11, 12 million years ago, what do we have? We actually have a rich fossil record, but most of it is in Southern Europe and in Asia, and some fossils in Africa as well. So our ape ancestors that would have branched off and evolved into gorillas, chimpanzees, and humans hugged the Mediterranean. And so it wasn't just Africa. It looks like Eurasia through the Middle East and into Southern Europe also was involved. And it's in part because the great forests of Africa, the tropical rainforests, at the time, 10, 11, 12 million years ago, hugged the Mediterranean. You have these vast forests in that area. And where there are forests, you're going to have apes. Now, as climate changed at that time, as it began to dry and cool, those forests began to recede. And they receded closer to the equator, and that's Africa. And so as those forests began to pull back towards the equator, the ancestors of gorillas and chimpanzees would have survived and done well in those kinds of environments, and the ancestors of humans. And so, why Africa? Well, our closest living relatives are African, chimpanzees, bonobos, and gorillas. And so that's a clue that most likely our oldest ancestors were there as well. But now we've been able to piece the story together using using fossils and using our understanding of how climate changed. And it shows that it was a little more complicated, that it wasn't always just Africa, that these apes also were in Europe. It's such a neat thing that we find fossil apes in France and Spain and Greece and Italy and Germany and Turkey and Hungary, places that don't have apes today, but they used to.
Okay, so you also mentioned that occasionally, and I don't know how often, you do a trip to Africa yourself searching for more fossils. So
Mm-hmm.
I wonder if you could describe, I mean, and I don't know if you consider this professional traveling or for pleasure, knowing you, it could be either or. But can you describe one of your trips? I mean, you go
Yeah.
to the field and what start just digging on the ground.
Oh, so these are professional trips. These
Okay.
are work trips. But boy, am I so lucky that my work trips take me to these absolutely extraordinary places in Eastern and South Africa. In South Africa, there are caves where fossils are found. It's a very different kind of circumstance, searching for fossils in caves. My most recent expedition was to Tanzania in Eastern Africa, and that was in 2019, before the pandemic started, at a site called Liatoli. And Liatoli is about 3.5 million years old. There are sediments that are much younger than that, but the oldest is about 3.5 million years old. We find fossils there of what's called Australopithecus afarensis. That's Lucy's species. She's been discovered at that site. But what's really special about that site are their fossilized footprints. There's a layer of volcanic ash that has that at the time, 3.5 million years ago, that ash mixed with some rain, and it formed this kind of mud-like substrate that animals walked through. Ancestors of elephants and giraffes and antelopes and zebras and the ancestors of humans walked through this ash, but then the sun came out and baked it, hardened it, and these footprints are preserved.
Wow.
They are amazing, amazing, amazing. And we spent some time working on them and finding some really, really outstanding prints that are complicating our picture of human evolution in a really fun and exciting way. And so at these sites, yeah, you don't just bring a shovel and randomly start digging. You actually let the rain do the work for you. So during the rainy season, rains will wash down these ancient hillsides, and they'll scrape away some of the soil, some of the dirt, and expose bones or fossils that have been preserved in those sediments. So then,
Wow.
when the rainy season ends, you then go to that site during the dry season, and look through those hillsides for those bones sort of sticking out of those
Wow.
hills. And if you find them, then you can start to
You
pull
become
out,
famous.
oh, well, usually they're fossils of zebras and antelopes and ancient warthogs, and but if you're lucky, sometimes you find fossils that have the anatomy that you recognize as being from an ancient human.
Wow.
And there's
That's
nothing
amazing.
like it.
I
Oh,
noticed in your
nothing like it. Go
I
ahead.
noticed
Yeah.
in your website that you have a MOOC course for people who are interested in this subject after listening to you speaking with so much passion about it. Can you tell us about that course?
Yeah, that course was done at Dartmouth, where I teach, and it is an open course. It's a MOOC. It's a massive online open course, so anyone can take it. It's entirely free, and it's a course that very much mirrors the elements that are in the book, and in fact inspired in many ways a lot of the writing that's in the book. I realized as I was going to write this book that I needed to rediscover my voice, a voice that can communicate scientific ideas to a general public. Um, and one of the ways that I was able to do that was by working with this really wonderful team at Dartmouth, writing these scripts for this online open course. And so it's called The Science of Upright Walking, Bipedalism X. And so if you look on my website or search what's called edX for the science of upright walking. You'll find this MOOC, and it's a self-paced course. You can start it and stop it. You can do it all in a couple days, or you can do it at your own pace. And that's what I like about these MOOCs. Yeah.
I love them too. Okay, so the last question is, can you tell us one more time the title of the book and where can the listeners follow you?
So the title of the book is called First Steps: How Upright Walking Made Us Human. It was published by HarperCollins, and it just came out April 6th, so it's been out for about 5 weeks now. And folks can look me up on my website and follow me that way with all sort of latest updates. I also have a Twitter handle. It's DeSilva_Jerry. Folks can follow me that way. We just had a new paper published that I posted there on Lucy and Lucy's skeleton, and we're still learning new things about these ancient bones.
So for the latest development of what happened 4 million years ago, we can follow you on Twitter.
That's right.
Jeremy, thank you so much for your time.
Thank you for having me. I appreciate it.